Equilibrium, last one. Reactions involving both forwards and reverse reaction taking place at the same rate. All observable properties like pH, things like that remain constant at equilibrium. Chemical equilibrium is dynamic equilibrium, which means basically it's changing at a molecular level. So little tiny atoms and molecules are rearranging. Of course, you don't see that happening, but that's in fact what's happening there. This really got probably, well, it's actually not too bad, I guess. A little bit messed up here, but its initial system is built, equilibrium system is placed by 0.424 molar N2, 0.808 into an empty flask. So we need to have our little ice table here. Boom, boom, boom. Boom, boom. 0.424 will go here. That's the N2, of course. 0.808 will go there. That's that part there. And 0 there. It says here at equilibrium we have 0.224. I said 22. 0.224. That is a decrease, therefore, of, let's see here, 0.2. And of course, if that's 0.2 decrease, this is going to decrease or get used up at a rate of 1 to 3 times as much. So that'd be a decrease of 0.6, I guess, molar. And that means that that would increase on a 1 to 2 level here. That would be a, what, 0.4 increase. So this will be 0.4, adding those up. This will be 0.208 there, and that'll be your equilibrium system there. Did I get that right? 208, yeah? Does that look good? I don't know why I have a different, I must have messed mine up. That's okay. 0.224. Yeah, okay. Good enough. We have to do what here? Kc for this reaction. So don't forget Kc, of course, would be, I'm just going to write this out once here. NH3, because I don't plan on doing this again here. Squared over, don't forget, this would be the equilibrium law, N2, and what else? H2. And that, of course, is to the third power there. Don't forget, you don't include the solids, you don't include liquids. So water's out, solids are out, anything else is fine there. So putting these numbers in here, let's see. We are going to have 0.4 squared over 0.224 and 0.208. And that should be also cubed. And if I did that, I think I'm going to get a slightly different number than the one I have written down here. So let me just do that real quick here. Squared divided by 0.224, 0.208 cubed, 79.4 should be your Kc value there, I believe. Is that right? No? Let's see here. Did I do that right? Yeah, I think so. Yeah? Just double check maybe. I don't know why I have like, that's not the number. Okay, I don't know why, I don't know how I got that number. That's not even close. Anyway, okay. All right. So Kc values, what do they tell you? Well, we'll talk about that on the next page here. Kc values are always greater than 0, but can range from very small to very large values. All right. Can range from very small to very large. When Kc is very small, there are many more reactants than products at equilibrium. So basically it favors reactants kind of thing. There's a lot more reactants than products. When it's very large, of course, we get a lot of products and not very much reactants. There's more more products than reactants. When Kc is close to 1, they're roughly about equal concentrations. And the value of Kc is temperature dependent. In fact, temperature is the only thing that affects Kc in those cases there. Okay? And then we did all these Le Chatelier principles here, and we have quite a few things to go over here with that. A system at equilibrium will respond to a stress that takes it out of equilibrium by attempting to minimize the effects of that stress. After the stress is imposed, the system will respond by either favoring the forwards or reverse reaction. So, no, this got messed up here, but you guys have it there anyway. This one here, if we, first of all, if we're going to do this, we have to know that this is the exothermic one, and this, of course, would be the endothermic one that way. And you have that equation written down there, but it's exo and endo that way. Once again, how would you find that out? Well, this is a formation reaction. N2 and H2 gives me NH3. So look that up in your data booklet, and you'll see the actual numbers there, whatever that happens to be. So forwards reaction is exothermic. The reverse reaction is endothermic. So if I take out H2, of course, I guess we need to sketch graphs for these, don't we? So for number 1, I'll call this number 1 here, 2, and 3. So here we go. If I'll try and make these a little bit smaller, perhaps. What do I need to develop? Concentration here, and then I guess we got some equilibrium stuff over here. So let me do them in the same order here. I'm going to do N2, H2, and NH3. I'll do them in that order there. N2, H2, NH3. Now, so this will be the initial part here. If I take out H2, so if I take out H2, of course, it is going to dip down. And then, of course, Le Chatelier's principle says, if I take that out, it wants to try and build that up again. So to build that H2 back up, I'm also going to be building up N2 as well. So I'm going to be building up some of that as well. There's no dip with that one, of course, because I didn't take out any or put any in. To make more N2 and H2, that means I got to use up NH3. Okay, and then it'll reach another equilibrium somewhere there. That'll be the equilibrium here. This is the shifting part, and this is the initial part. Okay, cooling the system down. Number 2, same thing. Let me start with get rid of that a little bit there. Okay, there's your initial part here. What did I say? N2, H2, NH3. And once again, if I cool the system down, cool it down. So if I cool it down, it tries to heat back up. Heat back up is exothermic. So if I cool it down, it's going to try and make more exothermic. Exothermic, of course, is the forwards reaction. I'm going to be making more NH3. So that's going to increase. There's no dip or anything like that. And that means I'm going to be using up H2 and N2. Oops, that should be straight there. And that'll be your equilibrium there. This is your shifting equilibrium, and this was your initial equilibrium there. Okay? And finally, the last one is compressing the system. Number 3 here, compress the system. Now, N2 I said, H2, NH3. So, first thing that's going to happen with these ones, if you compress the system, of course, the volume shrinks or gets smaller. If the volume goes down, the concentration goes up. So the first thing I need to have is a spike, up, up, up. The concentration goes up for all 3 of those in that case. And then, of course, when you compress or expand systems, it depends on the number of molecules on each side. This one, we have 4 molecules in total, 1 N2 and 3 H2, so that's 4. And 2 on the right-hand side. If we're compressing, it's going to favor the side with the least number of molecules, so it's going to favor the NH3. So I'm going to be making more NH3. I'm going to be using up H2 to do that, of course, and N2 to do that. And that'll be your final equilibrium here again. And this will be your shifting part. And this will be your initial here. Okay. So that's Le Chatelier's principle. Oh, autoionization of water, of course. Remember that every little bit of every water has some water has H3O plus and OH minus ions in it. The Kw for that is 1 × 10⁻14. Forms the basis of the pH and the OH scale, of course. Calculate the pH and pOH for a solution that has a hydronium ion of 2.5 × 10⁻10 molar. Well, if it has a pH of, find the pH, I guess. If we're talking about H3O plus, remember that is directly tied to pH, and we can take the negative log of 2.5 × 10⁻10, and that'll give me the pH of that, which works out to be apparently, there we go, yeah, 9.6 0, don't forget, I mean technically I know I sometimes skip over this, but 2 significant digits, so 2 after the pH. And of course, a couple ways you could figure this out. You could do, well, I'll do this. Hydroxide ion concentration, of course, gives me POH. If I wanted to do that, well, first things first, I'd have to use, like I said, there's a few ways you can do this. This is the more complicated way. If I wanted to find, what am I thinking here? If I wanted to find the hydroxide ion concentration, I need to take Kw divided by the H3O plus concentration, yes? So 1 times 10 to the negative 14 over 2.5 times 10 to the negative 10. That would give me the hydroxide ion concentration. I could do negative log of that. So if I did that concentration into here, negative log of, well, that concentration there, I guess, I'd get 4.40, 2 significant digits again. The easier way to do that, of course, is once you know pH, 14 minus 9.60 gives you 4.40. That's the easier way to do that, obviously. But if you know the hydronium ion concentration, you know the hydroxide ion concentration, 1 times 10 to the negative 14 is what this says right here. Not very clearly. And once again, you can flip back and forth between those two. If you want to find pH of a strong and weak acid, okay, well, might as well do the whole kit and caboodle here, I guess. Nitric acid is a strong acid, so when you react that, when it's placed into water, you will get H3O plus and nitrate ions. And of course, if this is a 0.10 molar concentration, then this is 0.10 molar because it is a strong acid. And if you take simply, you want the pH of that, you take the negative log of 0.10 and you'll get 1.00. Done. Easy. Strong acids, whatever the concentration of that is, that's what it is. For weak acids, HOCl, for example, hypochlorous acid, and water, you get H3O plus and hypochlorite ion, aqueous. And in fact, we need to make sure double arrow here because it doesn't all break up. It's in equilibrium. 0.10 molar here is not 0.10 molar there. I don't know what it is. And that's why you have the Ka value booklet, because of course the Ka is the acid ionization constant. It tells you basically the percentage that breaks up. So we put in 0.10 molar here. Ka in this one here works out to be 4 times 10 to the negative 8 is x squared over 0.1. X works out to be about 6.32 times 10 to the negative 5 moles per liter. And of course the pH would be the negative log of that. Works out to be 4.20, all said and done. Okay? So, you know, once again, we can see that even though both acids start out at 0.10 molar, one has a pH of 1, the other one has a pH of, well, 4.20, which is not really that close. It's quite a bit different. All right. Strong and weak bases. Once again, sodium hydroxide is a strong base. And when I put that into water, I get this. Dissociation, of course, is what this is called, yes. If I have 0.10 molar here, I have 0.10 molar there. That's how strong bases react, just like strong acids, of course. When I do this, I will take the POH, negative log of 0.10, and this would be, of course, 1 would be the POH, and then, of course, the pH, therefore, of this one would be 13. Don't forget, of course, when you have bases, you're finding the hydroxide concentration, and then you need to convert it to pH. If you're doing a weak base, well, I think it was what, sodium acetate. Well, ultimately it's acetate ions here, of course, is the weak base. React it with water because I don't have hydroxide, so it reacts with water. I get this here, hydrogen acetate and hydroxide, And once again, I'm going to have to do this kind of thing here. Don't forget now you need to use the KB value, x squared over 0.10, to figure that out. So find the Ka value in the data booklet, change it to KB. KB, by the way, is 1 times 10 to the negative 14 over 1.8 times 10 to the negative 5, which works out to be 5.5 times 10 to the negative 10 equals x squared over 0.10. X works out to be right over here, square root, of course, etc., times 10 to the negative 6. pOH of that is 5.129. Therefore, the pH is 8.87. And that should be your final answer there, I believe. Okay? So this would be the concentration of the hydroxide ion. And then, of course, we'll change it to hydronium. Bronsted-Lowry. This here kind of got messed up. Well, usually it does, but there we go. Okay. In a reaction, acid is a proton donor, base is a proton acceptor. In every equilibrium proton transfer, there will be 2 Bl acids, 2 Bl bases, and 2 conjugate acid-base pairs. In this case here, I guess we'll do that. Let's see here. This is your Bl Bronsted-Lowry acid. This is your Bronsted-Lowry base. And you could do this kind of thing here, H plus proton donor. In this case here, this would be your Bl acid. This would be your Bl base, proton donor, proton acceptor. Okay. Once again, there's 2 pairs here. There's 2 conjugate acid-base pairs, HCN. They differ by a proton, of course. That's your conjugate acid-base pairs, HCN and CN minus. And of course, H2CO3 would be your acid, and HCO3 minus is your conjugate base of that. Okay? Little definition thing there. Alrighty. Acid-base indicators. Mixture of a weak acid. One key important thing here, it's a weak acid and its conjugate base. It has to be weak. If it's strong, you can eliminate those right away. In which the acid HIN has a different color from the base IN minus. The indicator will take on a particular color depending on the pH of the solution into which it's placed. So the indicator will take on the color depending on which indicator it's placed into. Predicting acid-base reactions. Remember, the strongest acid donates an H plus to the SB. Products are favored when SA is above the SB in the table. Reactants are favored when the SA is below the SB. And of course, the reaction is quantitative when H2O reacts with OH minus. Or sometimes, in some cases, they'll tell you when it is in fact quantitative. So what they're saying is, if that's the strongest acid and that's the strongest base, that of course is a, well, we would say from before, it's a spontaneous reaction. In this case, products are favored, okay? And if it was the opposite, SA, and then the SB was up here, for example, the reactants are favored. Okay? Predicting acid-base reactions. So we have some sodium, Na plus, methanoate, which I believe is, I'm going to have to see, no, it's CH, isn't it? CHOO minus, yeah. Right? CHOO minus, and ascorbic acid. I guess I have these written down. So, yeah. And then ascorbic acid, of course, is H2C6H6O6. And of course, yes, there's some water with that as well. But strongest acid, of course, is the ascorbic acid. The strongest base you'll find is the methanoate. So we're going to react those two together. H2C6H6O6. And the the way that they have it, I think, in the data booklet is HCOO minus. Not that it really matters in the big scheme of things, but gives me proton donor, proton acceptor. So I'm going to get HC6H6O6 minus and HCOOH aqueous. So that's probably the most likely reaction there. And I actually don't have this written down, so I don't know if the products are favored here. Or which one here? Let me just double check here. Ascorbic acid, right there. And then the methanoate one is below it, I guess. Where is it here? Methanoate. No. Oh, methanoic acid's above there, yeah. So reactants are favored here. Reactants are favored or less than 50%. So you'd probably have more reactants than products in this case. So less than 50%. Hydrobromic acid. Hydrobromic is a strong acid, so when you see that, you really need to have those two things there. And then, of course, the sodium is the 1+, and the oxalate is a 2-. So those ones there. Let's see. Strongest acid, of course, and oxalate. And you will get H2O and H1-, like so. That's no there. Okay, and once again, you'd have to double check. I didn't write those ones down. That's got to be that's products favored there. I shouldn't have to look for that one. Products favored, greater than 50% reaction. So greater than 50%, probably more products than reactants, of course. Okay. pH curves next. Sketch and label a diagram of hydrochloric acid and sodium hydroxide. So with sodium hydroxide, so remember what goes where kind of thing. So if it does say this, we have to remember, is this the aliquot or the titrant or whatever kind of thing. So it's the titration of hydrochloric acid with sodium hydroxide. The sodium hydroxide, of course, is in the burette. So you're titrating it with this. That's the burette. This is the aliquot, and it's always in that order. Always, always. So basically they're saying the hydrochloric acid's in the bottom, the sodium hydroxide's in the burette. So if it's the hydrochloric acid is in the bottom of this part, the aliquot, we're going to start out low, and it's going to go like that. That right there, of course, should be exactly 7 because it is a strong acid and a strong base. And when you mix a strong acid and a strong base, you of course get water. So that will be at 7. So you can pick an appropriate indicator for that, like bromothymol blue would be a good one for that one because it's right in that range there. All right. Butanoic acid and sodium hydroxide. Well, butanoic acid looks like this. And sodium hydroxide, strong base, of course, gives me C3H7COO- and water. And this, of course, is a weak base here. Okay, so once again, pH curve. Let's see. So titration of butanoic acid with sodium hydroxide. Once again, this would be in the bottom part. This is your titrant here. So we're going to start low. Actually, with these ones, remember, it's got that little funny thing at the front, at the beginning here. It kind of goes like that, and then it takes off up like so. That right there, well, I can tell you that's probably 7 there. This is a pH greater than 7 somewhere. That right there, that's the endpoint, of course. And don't forget your equivalence point here. And once again, that's your endpoint there. Okay? Because you do form a weak base, so it's somewhere up there. Okay. Yeah. Then pH curve, sketch and label pH curve for the titration of ammonia with hydrochloric acid. So ammonia, of course, weak base, hydrochloric acid, strong acid. We'll get proton donor, proton acceptor, NH4 plus, and hydroxide. And if we're going to do a pH curve for this one, let's see, is this one going to switch now? So it's titration of ammonia, so ammonia is in the bottom, with hydrochloric acid. So probably going to start out fairly high here. It's going to dip down a little bit here and kind of level out, and then dip big time here, endpoint. This right here, of course, this is an acid, and this is your base here. It's a strong base. Let's see. Oh, sorry, that's not right. I should have got, I was thinking to myself, that didn't look great. Water here, that's better. That's water. H proton donor, proton acceptor there. That's better. So we do have an acid that works out here, so this will be a pH of less than 7. This will be the equivalence point down here, of course. And okay. Then we'll do one of these here. As soon as you see second endpoint, we know that it's got 2 endpoints, of course, which means basically it has to be polyprotic in order for that to happen. So sodium carbonate, once again, sodium doesn't really matter. That's the carbonate there with, of course, H3O+. Okay, so we're going to do titration of sodium carbonate. That's going to start in the bottom. The hydrochloric acid is going to be in the burette, so that is your titrant, of course. And we have to do 2 endpoints. So I'm getting tired of the red. So what did I say? Oh, let's see here. Sodium carbonate is what we're going to start with. So once again, it's going to get this little dip here. Down once, down twice, like so. And like that. At the first one here, at the first endpoint, we are going to have, of course, H3O plus and carbonate gives me proton donor, water, and HCO3 minus, aqueous. That'll be for that one right there. And the second one, of course, now that that's all, that proton has been quantitatively transferred, that's a quantitative reaction right there. We're going to take HCO3 minus now, or no, sorry, yeah, well, and the acid, I guess. I'll do the acid first. H3O plus and HCO3 minus gives me H2O and H2CO3. This one here, I can tell you for sure that pH is less than 7 because that's water, that's an acid for sure. So I know that that pH is less than 7. As far as this pH here, this endpoint one right here, that's a little tougher because that's water. That is not only a weak acid, but it's also a weak base. It's amphiprotic, so you'd have to look those 2 numbers up and decide what it's acting as. And I wish I could, I didn't actually do that, I guess, but maybe I will. HCO3 minus is a 4.7 times 10 to the negative 11 Ka value as an acid. If I want the weak, or if I want it to be as a base, don't forget you got to take 1 times 10 to the negative 14 divided by, and then you have to find it as a base, HCO3 minus. So I'm looking on the right hand side, and there it is there. Of course, the acid that goes with it, I'm looking at carbonic acid now. So HCO3 minus as a base would have a Kb value of 1 times 10 to the negative 14 divided by 4.5 times 10 to the negative 7. And I get 2.2 times 10 to the negative 8, roughly. So weak base it is then, I guess, because it's larger. So I would know that this pH has to be bigger than 7 in that case there. because it is acting as a weak base there. So that's that one there. And then, let's see, I think it's just the opposite for this next one. Phosphoric acid, once again, and sodium hydroxide. So, let's see here. I guess we'll do another graphy here. So we are doing it with sodium hydroxide. So we're starting out with the phosphoric acid. Once again, you'll kind of see this little, and then kind of like that. There's one, there's two. Don't forget this is the buffer region here, and this is the buffer region there. Let's see. First one, of course, this would be the phosphoric acid, which is a weak acid and a strong base. Gives me proton donor, proton acceptor, H2PO4, what is it? 1 minus, I guess, and water. And then for the second endpoint here, we now have H2PO4 minus and hydroxide to give me HPO4 2 minus and water. So proton donor, proton acceptor kind of stuff. Yeah, this once again, same kind of dealio. In fact, both of these I believe are amphiprotic if I'm not mistaken. So probably a lot of work to do with that, I imagine. Let's see. H2PO4 minus, starting at this one here, the Ka value for this is 6.2 times 10 to the negative 8. The Kb value for that, is there a Kb for that? Yeah. Well, it's 6.9 times 10 to the negative 3, but of course I got to take 1 times 10 to the negative 14 divided by 6.3 times 10 to the negative 4. And that's, yeah, not really a contest there, I didn't think so. Times 10 to the negative 11. So this is an acid here. Ka is larger. So this would be a pH less than 7. And this pH here, well, we're going to have to check it out. HPO4 2 minus is 6.2 times 10 to the negative 8. HPO4, where is it here? Where'd it go? Right there. HPO4 2 minus 6.2 times 10 to the negative 8. And no, that's not it. Yeah, that I think I screwed that one up actually. That's not it. I'm looking at the wrong one again. No. Let's do HPO4. Okay, HPO4 2 minus is 4.8 times 10 to the negative 13 for the Ka value. That's not very big. I pretty much almost guarantee you that the Kb value is going to be bigger than that, because that's pretty much as weak as an acid can get. So I imagine that that base, the opposite of that, not the opposite of that one, but I imagine that the other number's got to be pretty, well, bigger than compared to that. HPO4 2 minus must be closer to the top then. Oh yeah, it's not that much more. 6.2 times 10 to the negative 8 is the one I looked at before, but I got to take 1 times 10 to the negative 14 divided by 6.2. I might have done this already, I don't know. 1.6 times 10 to the negative 7. So yeah, not really competition there. It's definitely a Kb, so pH has to be greater than 7 for that endpoint there. All right, a couple, I don't know if we need to talk, do we talk about this at all here? I forget now. Well, I guess it's coming up here, but don't forget, once again, if that's X, then this has to be 2X there, all right? I'm sure, well, it's kind of coming up here with the acid-base stoichiometry, but, okay. Next, buffer is mixture of weak acid and its conjugate base. Can maintain a nearly constant pH when small amounts of H3O plus or OH minus added. pH of a buffer can be found using the Ka expression. Acid-base stoichiometry ratio can be determined by the number of endpoints in the reaction. If it's monoprotic, it's a 1-to-1. If it's polyprotic, then it could be a 2-to-1 or possibly even a 3-to-1 ratio. So when you look at something like this here, for example, once again, sodium doesn't really matter in this case here. We got our hydroxide there. That's, of course, our strong base. Here's a polyprotic acid. I know that right away because it's H2SO3. So I know that that's going to have probably a few endpoints, or 2 endpoints in that case there. So acid, probably the first thing I'd say is H2SO. I'll write it all out here, of course. Would give me HSO3 minus and H2O, like so. Then I have HSO3 minus and hydroxide to give me SO3 2 minus. And water again here. So when I add those two first endpoint, second endpoint equations up, I get a total of H2SO3 and 2 hydroxides. Gives me SO3 2 minus and 2 waters. And remember, that cancels with that, of course, and that's the overall net reaction that you want to be looking at. And that's important, don't forget that part. Concentration here is 0.245 molar. It says that this concentration is 0.173 molar, and I'm using 200 milliliters of it. So I can find N, I can move N over times 2, of course, don't forget, that's the important part there. And I can find V, the equivalence, what volume basically in this case they're asking for. So the equivalence point must be added to titrate to the second endpoint. So let's see, get about 0.0346 here, which means I get about 0.0692 there, and this works out to be about 282 liters, 0.282 liters to the second endpoint, which probably means that the first endpoint happened at 141, half as much, of course, right? Because we're going to the second endpoint, so once again we'd have to assume that x and 2x kind of thing. Yeah, and I think that's it for that. So other common questions with this stoichiometry thing here would be probably a similar type of question you could do a titration with, so you could average the volumes within 0.2, and then you could find, for example, the concentration of the hydroxide, or perhaps the concentration of the sulfurous acid in this one here. Okay, and I think that's it for that one, as far as I know. Yep. All right.